So membranes are pretty dynamic. They're pretty cool because of the fact that, well, they're involved in um, protecting cells and selecting what comes in and goes out of a cell. Now, we've learned about the major building blocks of membranes, and we've learned about some of those basic kind of simpler components, your fatty acids. But now let's get into, well, what does a membrane look like? You're probably familiar with a lipid bilayer, and you've probably heard or visualized the lipid bilayer looking something like this, where you've got these polar head groups and then these non-polar tails. Now, those non-polar tails, one of the things that I want to draw your attention to is typically you only have two of them. Why is that? Well, what are the major building blocks of membranes? Well, they are your glycerophospholipids. Glycero, okay, so those are your three carbons. Phospho, okay, so phospho. Okay, so your phospholipid, that's where you have that phosphate, O, P, O, 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 and then the group coming off of there, lipid. So that glycerophospholipid is coming off of the top of this, and these two tails are your fatty acids that make up those tails. So membranes, they have they're a barrier. They help kind of keep nutrients in, keep the good stuff in, keep the bad stuff out. They carry out energy transduction. They're involved in movement of a cell, motion of a cell. And whenever it comes to a membrane, there's three major structures that I kind of want you to visualize and be familiar with. You first have your micelle, then you have your bilayer, and then you have a liposome. Now, one of the things that I want to draw your attention to is I want you to think about a micelle and a liposome in comparison and contrast with one another. I'd like to draw your attention to the center of a micelle. I'm going to draw a red dot to that center. Now, what is kind of surrounding that red dot? Well, it's nothing but your nonpolar tails. Okay, so what that means is that the interior of a micelle, because keep in mind, this is in three dimensions, it's a sphere from the outside, but it's a polar exterior. But on the interior, it's very non-polar. Okay, now if we compare and contrast that with the liposome, this is also spherical. That central cavity, though, it's not lined up with non-polar tails, but rather polar head groups. Okay, because we basically have a bilayer here. It's almost like, well, it's basically kind of a scaled down or a smaller version of a cell in some respects. Now, if you think about a cell as a whole, that's where you have your lipid bilayer, where you've got this very hydrophobic and nonpolar region on the interior, which is similar to this region right here of the liposome. But on the exact interior of that liposome, you have a spherical aqueous polar environment. Okay, I always like to compare and contrast the micelle and the liposome. A micelle has a nonpolar interior, whereas a liposome has a polar interior, or polar or aqueous interior. Now, in terms of how the different components of a bilayer or a membrane can move, we have what is known as transverse diffusion. Okay, this version on the top, what I'd like you to visualize is this um, blue-headed glycerophospholipid, we'll say. Now, that is on one side, one leaflet. We'll call it the inner leaflet. So just imagine that this is something that is on the interior of a cell. Now, on the bottom half, this is the outer leaflet. Well, we had this polar head group move down to the other side, to this location right here. That's going to happen, but it's going to happen very slowly. Now, if that lipid or that polar head group moves to a different location within the same leaflet, that's going to happen pretty easily and pretty quickly. I always kind of envision this as being like if you go to a concert and you're in the general admission area, well, you can move around a little bit, and it just takes a little time. If you're going from this part of the general admission area to that part, yeah, you're going to bump into people along the way, but you'll get there eventually. Now, this model at the top is known as transverse diffusion. So from going from the inner leaflet to the outer leaflet, that can happen very slowly, whereas this lateral diffusion happens pretty quickly. Now, one of the important things about a lipid bilayer and a membrane as a whole is that it's going to have a level of fluidity. And I always kind of think about the fluidity as like a structural integrity. It's going to be strong, but not immobile because it's a membrane. It's got to move, but it can't move so much that it has nothing to hold on to. So there's a temperature dependence on the fluidity of a bilayer. Whenever the temperature is very low, you're going to have this paracrystalline state. This is a gel-like state, whereas whenever heat has been added, then that gel transitions to a more fluid state. There's a little bit, or there's a lot more motion. Now, whenever this is below the transition temperature, so whenever the temperature is low, you have that paracrystalline state, whereas in the temperature is higher, and I'm saying higher, not high, but when it's higher, you're in this fluid state. Now, if the temperature gets too high, well, what happens to that fluid state? That just kind of blows up and falls apart. Above that transition temperature, you have that liquid crystal state at the bottom, the fluid liquid crystal state. Transition temperature is dependent on, this is very important, dependent on the chain length and the degree of saturation of the component fatty acid residues. Now let's think about that. We learned about the physical properties of fatty acids. Well, we had saturated fatty acids that, well, those remained, if you had a 16 carbon long, 16 colon 0, 16 carbons, 18 carbon colon 0, 16, 18 carbons with no double bonds, well, that is going to have a melting temperature of like 70 degrees or higher. But then whenever you had something like 16 colon 1 with a single double bond in there, a single degree of unsaturation, well, then all of a sudden your melting temperature dropped down to like 13 degrees or so. Now, in our cells, things like cholesterol, which is a non-membrane component or a non-membrane molecule that is a lipid, cholesterol can broaden the temperature range of that phase transition. So cholesterol influences the fluidity of that. The higher cholesterol is going to make it more rigid. A lower cholesterol level is going to make it a little bit more fluid. Now, there are organisms like E. coli, bacteria, for example, that doesn't really have things like cholesterol, but they still do serve as a great model for studying fatty acids in membranes. Now, this figure right here is from a paper from 1962. And in this paper, what the authors did was they grew E. coli at four different temperatures, 10, 20, 30, and 40 degrees Celsius. The ideal growth temperature for E. coli is about 37 degrees Celsius. Now, that's optimal. Okay. Will E. coli grow at all of these temperatures? Yes, it will. At a lower temperature, it's going to grow very, very slowly. At 40 degrees, it's going to grow a little bit faster, maybe, but also the rate of cell death is going to be a little bit higher. Now, what the authors of this study learned throughout this was, or sorry, what they measured throughout this was they measured the abundance, and I'm just going to focus on four of them. They looked at the abundance of myristic acid, which is 14 carbons and no double bonds, palmitic acid, 16 carbons, no double bonds. Then they looked at palmitoleic and oleic acid. These are monounsaturated fatty acids. And what they observed was that I'm going to just compare 10 and 40 degrees. At 10 degrees Celsius, the percentage of fatty acids that were 14 and 16 carbons with no double bonds, completely saturated, was about 22% of fatty acids were that. At, whereas the monounsaturated accounted for 64%. Okay, 64% of the fatty acids that were detected in these bacteria, presumably from their membranes, were monounsaturated. Okay, so we've got monounsaturated, which they're more than likely going to be a liquid at room temperature compared to the saturated, which were absolutely a solid at room temperature. And they calculated a ratio. The degree or the ratio of unsaturated to saturated was 2.9. Okay, so there were more unsaturated fatty acids at 10 degrees than the saturated fatty acids. So they also looked at Well, let's see the distribution of these same fatty acids at 40 degrees. 56% of fatty acids at 40 degrees Celsius were saturated. 21% were your monounsaturated fatty acids. So they saw almost an inversion. The ratio was 0.38. Okay, now let's think about this again. This monounsaturated got cut basically, it got divided basically by three. So a third, yeah. Um, at low temperatures, they favored monounsaturated. High temperatures, by comparison, favored saturated fatty acids. Okay. So if we think about this, the saturated fatty acids, they're more than likely going to be a solid at room temperature or at 37 degrees. We're getting closer to them being a little bit more liquefied. So if it was just monounsaturated fatty acids at 40 degrees, well, there'd be no integrity to that. That that membrane would completely fall apart. So you have to have a combination of monounsaturated and saturated. And it just so happens that, well, actually, heck, if we tried to build a membrane with these exact numbers at 40 degrees Celsius, that membrane would fall apart immediately because there's not enough of the monounsaturated, or there's not enough of the saturated fatty acids to hold it intact at 40 degrees Celsius. There's too many monounsaturated fatty acids. Whereas this ratio, well, that's the ideal for 40 degrees Celsius. If we shifted this to 10 degrees Celsius, that membrane would be too rigid. There'd be no movement. So you kind of have to strike this fine line, or walk this fine line and strike this balance of what gives you a combination that makes your membrane fluid, but not so fluid that it falls apart, and not so rigid that it can't move. So that's all what's being juggled here. Now, when it comes to the distribution of different lipid components in the inner and outer leaflet of a lipid bilayer, well, the distribution of your total phospholipids, it's 50-50. Okay, so it's not like the inner leaflet is thicker than the outer leaflet. It's an even distribution. Now, the components, here we have three glycerophospholipids. And it's not so important that you know what these are, but recognize that the distribution of them is not even. Phosphatidylcholine, phosphatidylethanolamine, phosphatidylserine. Well, phosphatidylcholine, ethanolamine, and serine, well, this is what is shown on the inside of the membrane. Now, under some circumstances, what might happen is this phosphatidylethanolamine, you might have to flip it out. Likewise, this phosphatidylserine, you might have to move that to be on the outer leaflet for some communication mechanism. Now, that lipid asymmetry and that redistribution of those lipids, well, phospholipids are synthesized near the interior of the membrane. Now, there are two mechanisms to get those phospholipids from one side of the membrane to the other. We already talked about this with respect to this graph right here, that transverse diffusion, to get them from one side to the other. There's two ways in which to do that, and that's what we're going to talk about right here. There are enzymes known as flipases. They catalyze the flip-flop of specific phospholipids in what is known as a facilitated diffusion, so movement from you're on the inner side of the membrane to the outer side of the membrane. That looks like this. We've got our uncatalyzed movement. This is going to take it's going to take a very long time. This enzyme right here is an example of a flipase. And effectively what it does is it's going to bind to the selected phospholipid and move it to the other side of the membrane. Now, Flipases tend to equilibrate the distribution of their corresponding phospholipids across the bilayer. So they reach an equilibrium of here's the right number to have on the inner leaflet and here's the right number to have on the outer leaflet. Now, phospholipid translocases transport specific phospholipids across a bilayer in a process that is driven by the hydrolysis of ATP. Translocases can establish a non-equilibrium distribution of the phospholipid. So if I always kind of think about this as, well, if there's a reason to have a lot of one particular phospholipid on one side of the membrane or the other, a translocase is likely involved to say, oh, we've got to get all the phosphatidylserine displayed outward. That translocase is going to come along to all those phosphatidylserines and say, you're on the wrong side, and flip them all to the outer leaflet. Now, your biological membranes, we've already talked about glycerophospholipids, sphingolipids as major membrane components, but they also contain proteins. Proteins catalyze reactions, mediate the flux of nutrients and waste, and participate in relaying external information into the cell. Now, the protein to lipid ratios vary with membrane functions. So here are some examples of different cell types and different distributions. Now, E. coli, I mentioned previously that E. coli doesn't have any cholesterol. So this last column here, sterols, that's why that's at 0. But then what's kind of interesting is that 75% of an E. coli membrane is protein. Huh. So I think that whenever I think of a lipid bilayer, and maybe I'm not even necessarily thinking about a E. coli cell, but if I think about like a mouse liver cell, 45% of that weight is protein. 27%, less than a third, is phospholipids. 25% is cholesterol. Man, there's a lot of other stuff in a membrane that is not just glycerophospholipids and sphingolipids. There's lots of cholesterol, there's lots of proteins there. Now, what this ultimately is going to give rise to is a structure or a phospholipid bilayer known as a fluid matrix. The bilayer is a two-dimensional solvent, and it's got a bunch of stuff in there. The primary culprits are your proteins, your phospholipids, and cholesterols. Lipids and proteins can undergo rotational and lateral movement. Membranes are asymmetric. What that means is that stuff that's displayed on the outside is not necessarily displayed on the inside. And a good example of that is a glycolipid here. A glycolipid is a sugar that is covalently bound to a lipid. Now, each one of these rings right here corresponds to, well, a sugar like glucose or galactose or mannose or maltose. These are tools that are used to communicate with like other cells. So this is what is displayed outside of the cell. Now notice those glycolipids are not found on the inside half or the inner leaflet of that. In addition to that, outside of the cell, you've got oligosaccharide chains on glycoproteins. So that is sugars that have been modified or have been added to proteins, again, as a mechanism for communication. And last but not least, a major thing that you're going to have outside of the cell is, well, just a polypeptide, a part of a protein. So when you think about the outside of the cell, I always think about sugar and protein. Those are the two things that are kind of the big tools that are at a cell's disposal. Now, on the inside, we've got proteins. We've got proteins that are integral proteins that are a part of a membrane protein. So something that a polypeptide that spans a membrane, and that is a single transmembrane helix. We've also got sterols, like cholesterol. Then we've got peripheral proteins linked to a lipid. We'll get more into that after a little while. Then we've got integral proteins with multiple transmembrane helices. So we've got multiple of these helices. So we've got, think about this as the N termini of a protein. This is the C termini. This protein goes into the membrane, loops around, comes back, loops around, goes back, loops around, comes back. So this is multiple helices to kind of thread in and out of that lipid bilayer. And those In this case, what we're seeing is the N and C termini is on the same side, both on the interior. That's not always the case, but that's what we're seeing right here.